Hello everybody, today let's talk about the Moivre's theorem. Now in our previous lesson, I showed you that if you have a complex number z1 written in its polar form and another one z2 written in its complex form, in its polar form, and you're asked to multiply them, all you need to do is you multiply their moduli and you add their arguments. Okay, in the same way, if you have a complex number z written in its polar form, okay, and you want to multiply it by itself, meaning that you'll have z, you'll have r multiply by r theta, that you're multiplying z by itself, meaning z squared. Okay, now from this analogy up here, you will multiply the moduli and you will add their arguments. Okay, so this will be r squared theta plus theta is 2 theta, that is z squared. What about z cubed? Z cubed will be r theta multiplied by r, okay, and multiplied by, since it's multiplication, we multiply the moduli, r multiplied by r multiplied by r, and you add the arguments. Okay, so this will be cubed theta plus theta plus theta is 3 theta. Okay, what about z raised to power 4? Z raised to power 4 will be r theta multiplied by r theta. Remember, this is z in polar form, and we are raising z to power 4, meaning that z will appear 4 times. Okay, times that. Again, you multiply their moduli, and you add the arguments. Okay, r times r times r times r is r power 4 on the argument theta plus theta plus theta plus theta, that is 4 theta. So the pattern emerging here, if you are keen, the pattern emerging here is that if you have a complex number z and it's raised to power n, Okay, if you have a complex number z raised to power n, so meaning that the result will be r raised to power n, and the argument will be like that. This means that if you have a complex number raised to power n, the result will be the modulus r raised to power n, and the argument is multiplied by that n. Okay, and these people is the basis of the Moivre's theorem. This is the basis of the Moivre's theorem. Okay, remember, if you have a complex number z raised to power n, you will raise the moduli by n, and you will multiply the argument by that n. Okay, and this is true. It is true for all positive negative and fractional values of n. Okay, so let's try an example. Let's try an actual example. If you have a complex number 4 and argument of 30 raised to power 4, okay, this will be 4 raised to power 4. The argument will be 4 times 30. Okay, this will be 256, and the argument will be 120. Okay, 4, it will be 4, because this is the value of our n is 4. You raise that 4 with the moduli with that 4, get to 56, and you multiply the argument by that 4. So straightforward, that is our new complex number polar form. Let's try another example. Let's try 2 actually. Let's say a, so we have complex number that 2 power 5, and we have b have 2 plus 3j is to power 6. Okay, so as for a, our n is 5. Okay, our modulus is 2, and our argument is 35 degrees. So all we do is raise 2 by n, which is 5, and the argument is 35 multiplied by 5. Okay, so 2 raised to the power is 32, and the argument 35 times 5 is 175. Okay, as for B, now for B we have to be careful. It is written in B is written in Cartesian rectangular form. So first step we have to convert it into polar form, and by converting it into polar form, we need to start off with a sketch first. Remember what we said, it's always good to sketch. So we make a sketch first. Imaginary axis. This is our real axis. Minus 2, we know it's somewhere there. 3, we know it should be somewhere there. So drop that. Yes. So this is our complex number, minus 2 plus 3j. Minus 2 plus 3j. That is our complex number. Now, in order to convert it, we need to know the argument. In order to convert it into polar form, we need to know the argument. And the argument, remember how we defined it? It is the angle between the complex number itself and the positive real axis. Positive real axis of the Argand diagram. So this is the argument. This is the angle that we should find. But it is easier to find this angle since we already have the right angle triangle here. We just get this angle, then subtract it from 180 and we'll get our actual argument. Let's do that. So in order to get this, use tan. Tan phi will be equal to, opposite is 3 over minus 2. Okay, so angle phi will be equal to tan inverse of 3 over, okay, punch that in your calculator and punch that in your calculator. Tan inverse of 3 over 2. So this is 56.31 degrees. That is this angle, but we are not interested. We only want this. We want the argument, and this is the argument. Angle subtended from the positive real axis to the complex number itself. This is why it is always important to make a sketch so that you can know exactly what you are doing. So in order to get this, we need to do 180 degrees minus 56.31 degrees, and that angle is 123.06 0.69 degrees. So this is our argument. Theta, which is our argument, is 123.69 degrees. Okay. Now, next step, we need to find the modulus R. The modulus R is the square root. Since this is R, this is what is R, is the hypotenuse. So all you need to do is find the square root of the base squared and the height squared. Is 2 squared plus 3 squared. So that will be squared plus 3 squared. This will be, answer is 3.61. Now that is the modulus. The modulus is 3.61. Okay. Now we can write it. We can finally write it in. Polar form. So the modulus is 3.61 and the argument is 123.69. We have to raise it to power 6. Okay. Now we are ready to apply the Moivre's theorem. We are ready to apply the Moivre's theorem. And what does the Moivre's theorem say? You have a complex number like this raised to a power n. Our n is 6. You raise the modulus to that power 6, and you multiply 6 with 1, the argument, which is that. Okay. Now that is 3.61 raised to power 6. See, this will be 2, 1, 3.31, 6 multiplied by 123.69. This will be 742.14. Okay. But so this is our new modulus, and this is our new argument. But remember what we said: argument of a complex number lies between minus 180 degrees to 180 degrees. So we need to get it into this range. Now notice that 724 exceeds 360. Okay. So what we do, we notice that, look at our Argand diagram. If you go, this is the positive. If you go in the anti-clockwise direction, this is positive. One revolution, that is 360. Okay, one revolution, 360. Since our argument is 742.14, it means that it has gone once and twice. So what we do, you do 742.14 minus 360. What do you get? 36724 742.14 minus 360, that is 380.1. This one is still more than 360, so do again. 382.14 minus 360, this is 22.14 degrees. Okay, that means that it has gone twice. It has gone twice around the Argand diagram. It has gone once, that's one 360, and another 360, and then you add this to 22.14. So 1 360, 2 360, and then 22.14 will be somewhere here. The new complex number will lie somewhere here. Okay, so our new complex number will be the the modulus we got here. It will be 2213.31, and the argument will be 22.14 degrees. Okay, now it is in range. It is in the range of the conventional complex number. Okay, that is the modulus, that is the argument. And just by that, so since you know that the modulus, the argument is 22, it lie here it lies somewhere in the first quadrant. Okay, good. So let me leave you with an exercise to attempt on your own. Go and attempt this. Minus 16 minus 9j power 6, and you are to find that. Okay, go and solve this one, and I will give you the solutions, the answer together with the solution in our next exercise, in the next lesson. Thank you for staying with me. This is Understanding Math. Thank you.